All right, welcome back everybody. Here we are for video 2 of section 1014, finding Taylor and Maclaurin series for functions. All right, we left off, we had looked at groups 1 and 2. Here's group 3, a couple of Maclaurin series that might be helpful at some points in time, but we probably don't necessarily need to know them for this course. They're nice to know, but it's not something that you need to know. We've got the Maclaurin series for the function natural log of quantity 1 plus x. Which looks like that, and has an interval of convergence from -1 to 1, including the endpoint at 1. And then we've got this series, the arctangent of x, for the arctangent of x, and that's interval of convergence is from -1 to 1, including both of the endpoints. So those are two more series that are helpful to know, can be fairly commonly used, but they're not ones that generally we're going to expect you to know for this class. All right. By the way, this last series, very cool way we can use this, and we've used this idea in the past. The arctangent of 1 is equal to pi over 4. And using this series, we can express the arctangent of 1 as, let's put 1 in here for x, 1 minus 1 cubed over 3 plus 1 to the 5th over 5 minus 1 to the 7th over 7 plus 1 to the 9th over 9, etc. 1 to the 11th over 11, so on and so forth. A series of this form. That's equal to pi over 4. And so if we take this series and multiply it by 4, we get pi. And so going back to, using the summation like we have on our calculator in the past, we can find the sum of this for a bunch of terms. We could go ahead and program this series into our calculator. Sorry, I hit the wrong thing there. So if I take 4 times the sum of quantity -1 to the x times 1 to the 2n plus 2x plus 1. I don't need to raise, that's always going to be 1, divided by the quantity 2x plus 1. And I can add up the first 100 terms of this. Oh, I must have missed a parenthesis somewhere. Oh yeah, I'm missing a parenthesis here. No, wait a second. 4 times sum, there's -1 to the x. We close that off. Did I miss the parenthesis? I've got a parenthesis. Where am I missing a parenthesis here? Oh, no, I just forgot my variable. Oops. Sorry about that. And we can sum up the first 100 terms. I hate when I can't find, when I type something in wrong and I can't find out what's going on. Something went wrong here. -1 to the x. There's 1. What did I miss here? Did I type something in wrong again? Or is it my calculator incapable of doing this computation? What happened here? Oh, it's the sum from 0. I don't know if that does that make that big of a difference? Yeah, it does, because that 0th term is 1, so that's going to add up to 4. So we're going to add 4. There we go. And you see with 100 terms, I was like, what did I do wrong? 3.151493. So it's getting pretty close with 100 terms to the value of pi. The more terms we choose, the closer it's going to get. I'm going to go ahead and let it run. But this is an old school way that people used to approximate pi, was adding up this infinite sum. So that's kind of cool. All right. Continuing on, if we know all of these common Maclaurin series, we can very quickly and easily find other Maclaurin series by performing some transformations on those series. For instance, we can add, subtract, or multiply them by constants or powers of x. We can do division. We can take derivatives or integrals of things and arrive at new Maclaurin series. Basically, we can do a lot of very different things to series to arrive at other series to represent other related functions to the ones that we know. All right, let's start by looking at example 1, part A. We're going to find the series for the cosine of the quantity 2x. All right, so first of all, the series that I know related to this one is that cosine of x is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, etc., etc. My general term is going to be the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n over the quantity 2n factorial. I do not need my summation in my general term. This is a general term, not the entire series. Sorry about that. My brain slipped there for a little. So there's the series for cosine of x. And so we can very quickly and easily come up with the series for cosine of 2x by just substituting 2x into this series everywhere where there's an x. So my series for cosine of 2x is going to be 1 minus the quantity 2x, quantity squared, over 2 factorial, plus the quantity 2x to the 4th over 4 factorial, minus the quantity 2x to the 6th over 6 factorial. And I didn't specify the number of terms that I wanted here, so let's just write 4 and the general term. And then I could go ahead and simplify this and say that the series for cosine of 2x is 1 minus 2x squared, and this is going to be, let's see, 2 to the 4th is 16, 4 factorial is 24, so that's going to be 2/3 x to the 4th. 2 to the 6th is 64, and 6 factorial is 720, 64 over 720. I don't feel like doing that in my head right now, I'm sorry. Feeling a little lazy. That's 4 over 45, x to the 6th. And then with my general term, I prefer when I have something like 2x to the 2n, I prefer to split that out into 2 to the 2n, x to the 2n, because if I'm, depending on how much I'm doing with this, I might want to, deal with one of these individually. But there we go. There's a series for cosine of 2x. Now, as far as identifying the interval of convergence, normally the interval of convergence for cosine of x is that x is between infinity and negative infinity and infinity. So now, in order to find the interval of convergence for this, I would just say that 2x has to be in between negative infinity and infinity. And dividing all three parts by 2, negative infinity divided by 2 is negative infinity. And so this is our interval of convergence for the series that we found. It's from negative infinity to infinity. All right. Let's do one more at least. Part B, I'm going to come up with a series for 1 plus the sine of 2x over 2. Now this is going to take a couple of steps for me. I start with the series for sine of x, which is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And my general term is going to be negative 1 to the n, x to the 2n plus 1, all over the quantity 2n plus 1 factorial. All right. So now I'm going to break this down into parts. Like, as I operate here, I've got the series for sine of x. I'm going to go ahead and substitute 2x in there. Then I'm going to add 1 to the result of that, and then I'm going to divide all of that by 2. So first, the series for sine of 2x. I put 2x's everywhere. Everywhere where there is a x. Then I'm going to add 1 to this, which really just means I'm going to add 1 on the front end. I'm not even going to bother rewriting all that. I'm just going to go ahead and put that 1 in front. And then to get 1 plus sine of 2x over 2, I'm going to take that series and divide everything by 2. So this is going to be 1/2 plus x minus, let's see, 8 over 6 divided by 2, that's 8 over 12, so that's going to be 2/3 x cubed. And this is 32 over 120, 32 over 240. That's 2/15. I've got 4 terms now, so I'm just going to go ahead and roll to my general term. And adding 1 didn't impact the general term at all, but dividing by 2 will. And so this ends up being, I keep forgetting that n, -1 to the n times 2 to the 2n. It was going to be 2 to the 2n plus 1, but now we're dividing that by 2, so we take one of the 2's away from that. X to the 2n plus 1, all over 2n plus 1 factorial. All right, and as far as my interval of convergence goes, adding 1 doesn't change the interval of convergence. Dividing by 2 doesn't change the interval of convergence of the series. The only thing that could have possibly changed the interval of convergence was substituting the 2x in, and when I do that, I go from, again, we start with an interval of convergence of -infinity to infinity, so putting 2x in here instead of x, I end up with the same interval of convergence. It's just going to be -infinity to infinity. All right, we'll come back next time and do a third video on this unit to get through the last couple of examples. We still have a few more examples of working our way through these series to get through, and we'll do that next time. So join us then. Have a great rest of your day, everybody, and we'll see you next time. Bye-bye.